a lot of students see this maybe for the first time in like 8th grade. Like you're probably really familiar with this. You've probably seen this a lot. But I think it's very rare that students see a proof, or if you have seen a proof, maybe you don't remember it. And so the proof goes like this for the Pythagorean theorem. How did they know with certainty back in like ancient Greece that the Pythagorean theorem was true? And it wasn't just ancient Greece, but like the Pythagorean theorem shows up in a lot of ancient cultures that were developed like independently, right? They weren't in communication with each other. The Western hemisphere and the Eastern hemisphere weren't like talking to each other, but we still find, evidence that the ancient Native Americans of many different civilizations knew about the Pythagorean theorem, and like the ancient Sumerians and the ancient Chinese and everything, they all developed the Pythagorean theorem independently. And the way the proof goes is, say this is a square. So imagine I have, the required utensils to draw a square. I've got like a straight edge, I've got like a measuring stick or a string of a certain length, and I've got a right angle. So I can go ahead and construct a square. Well, then what I'd like to do is I'd like to measure some distance here and put a dot, and measure the same distance from the top right corner and put a dot, and the same distance from the bottom right corner and put a dot, and then measure the same distance from the bottom left corner and put a dot. So that this is all the same distance. And let's call this distance A. And so A is like the distance from here to here. And the distance that remains from here up to the other side is going to be called B. And since the total side length is the same on all sides of the square, then the remaining side length is B for the rest of it too. Now what I'm going to do is connect those green dots with a straight line segment. And if you remember taking high school geometry, one of the things you talk about in high school geometry is the theorems for similar triangles. You might remember like the side angle side theorem, SAS theorem. Side angle side says if two triangles have the same two sides and the angle in between those sides, if those are all exactly the same, then the triangles are congruent. And so that means all four of these triangles are congruent triangles because they have the same side angle side. They've got side length A, right angle, side length B. So by the side angle side theorem, these are all congruent triangles. They all have the same hypotenuse length, and that hypotenuse length is C. So now I know that this blue shape, this blue quadrilateral I just drew in the center, it's at least a rhombus. I don't necessarily know that the blue shape is a square, but I do know that all the side lengths are the same. And so a quadrilateral where all the side lengths are the same, that's called a rhombus. A square is a special kind of rhombus. So this could be a square. We don't necessarily know that this is a square. Another thing I could draw in from like high school geometry is like if I wanted to name this angle beta and name this angle alpha. And of course, these are congruent triangles. So this is beta and this is alpha. And this is beta and this is alpha as far as angle measures. Beta, alpha, all around. What is the sum of all of the interior angles of a triangle? Yeah, it has to be 180 degrees. And so 90 degrees plus alpha plus beta equals 180 degrees. That means alpha plus beta has to be equal to 90 degrees. Alpha plus beta is equal to 90 degrees. What else do we know? If I had like a setup like this where here's an angle here's an angle, and then here's a third angle. And these are all angles that add up to like one straight line. What is the sum of all of these angles, theta 1, theta 2, theta 3? What do those add up to? 180. And so now let's zoom in to a part of this picture, right here, where I've got alpha plus beta plus a missing angle is going to give me this straight purple line. So if alpha and beta add up to 90 degrees, and all three of these angles add up to 180, what does the middle blue angle have to be? 90. Okay, so now I know that this is a 90-degree right angle here. And because this is symmetric on all four sides, I've got alpha plus beta plus the missing angle equals a straight line, then all of these angles are 90-degree angles. And now we actually know that this is a square. And the rest of the proof goes like this. We say, I want to calculate the total area of the purple square. And I'm going to calculate this total area two different ways. And no matter how I choose to calculate the total area of this purple square, it should give me the same number. One way I'm going to do this is by multiplying the height by the base, right? Pretend it's just a big purple rectangle. And of course, the base of this rectangle is the side A plus B, and the height of this rectangle is the side A plus B. So if I multiply those together, I get the total area. And then on the right side, the other way I would like to calculate this total area is by adding up, what would it look like to add up 4 of these congruent triangles plus the area of the square in the center? Well, the area of the square in the center is c squared, right? What is the area of one of these congruent triangles?
1/2 BA.
Right, the area of a triangle is 1/2 base times height. And this time the base is b and the height is a, so I've got like, 1/2 times a times b, 1/2 times b times a, or whatever. But this is two ways of calculating the area of this purple square. And since it's the same area, they have to be equal to each other. And the rest of the proof is super duper easy little algebra. We've got a times a, I'm just foiling this out, 2a times b plus b squared. And on the right side, 4 times 1/2 is 2. Yeah. Carter's got it. I just subtract 2ab from both sides as my final step, and I get that a squared plus b squared is equal to c squared. And now the last thing to recognize is that when I start off by drawing a purple square, that ensures that my triangle has to have a right angle. And then whenever I measured some distance away from the corner and I put a dot, I could have made that distance whatever I wanted to, and it wouldn't change the remainder of the proof, right? I could have made that distance shorter, I could have made that distance longer, I could have made the whole square bigger, I could have made the whole square smaller. So it's completely general. It was arbitrary the way we chose the length of A and B. The only thing that we had to do is keep a right angle. And so we say this is true for all right triangles, no matter what side lengths A and B are. Because, if you were like, hey, I think that a squared plus b squared equals c squared is true for right triangles. You could maybe gather evidence for this by just finding examples like, oh, look, I just discovered that like a 3, 4, 5 right triangle includes a right angle by like drawing it and measuring it. Or I just discovered that like a 5, 12, 13 triangle includes a right angle because I drew it and I measured the angle. Right? That would be like evidence for this, but if you really wanted to prove that it's always true in the case of every right triangle, then this is how you might logically prove that. All right, you guys have seen this before. If you wanted to prove this trigonometric identity, that cosine squared plus sine squared is equal to 1, here's what you do. First, draw a triangle. And for this triangle, the hypotenuse is going to be 1. This angle is going to be theta, and this is going to be a right angle. Then what is this side length? Some of you guys have forgotten your trigonometry.
Was it sine of theta?
Yes, sine of theta. Because the definition of sine is that it is the opposite side length divided by the hypotenuse. And the hypotenuse in this case is 1, so the opposite side divided by 1 is the opposite side. And so that means the opposite side from the theta angle is sine divided by 1, or just sine. And then, what's this side length? Cosine. You had a 50-50 shot, right? This is going to be cosine of theta, because the definition of cosine is adjacent side length divided by hypotenuse for a right triangle. And this time the hypotenuse is 1, so the adjacent side length is equal to the cosine of theta, and this is obviously the side that's adjacent to the angle theta. And then the last step is to recognize that, hey, since this is a right triangle, then the Pythagorean theorem must apply. And the Pythagorean theorem implies that the squares of the side lengths added together will give me the square of the hypotenuse. And the hypotenuse is 1, and 1 squared is just 1, right? So this is an identity from trigonometry that just follows from the definition of sine and cosine. And if you draw this triangle with hypotenuse 1, you can see it has to be true according to the Pythagorean theorem. These are called the angle sum identities for sine and cosine because in the argument of sine and in the argument of cosine, I'm adding together two angles like alpha plus beta. We can prove this theorem by drawing a picture. And in my picture, this is a line segment of length 1. And I'm going to draw two other sort of line segments like this, to where this blue line is straight vertical, where it's supposed to be anyways. The long black horizontal line is supposed to be flat and horizontal, so that this makes a 90-degree angle. I will try to switch colors as often as I can to be more clear about which line segments I'm talking about, but I'm also going to connect this and this. And I want that to actually be a 90-degree angle, and I didn't draw it very well. But what I would really like is to have a 90-degree angle from here to here. And maybe I'll choose a different color because I'm going to verbally refer to these lines, and so I want you to know what I'm talking about. I'm going to then label these angles, angle alpha and angle beta, and that makes the length of this segment from here to here well, let's not do that first, I guess. Let's do this one first. This line segment from this point to this point is going to have a length of cosine beta. In other words, this black line segment has a length of cosine beta because cosine is the ratio of the adjacent side length to the hypotenuse. And so the adjacent side length divided by 1 is cosine of beta, and that means cosine of beta is the adjacent side length, like I've labeled it here. Now, because sine of alpha, and sine by definition is the ratio of the, oh, sorry, I should have said cosine, huh? Let me think about this again. Cosine of alpha is the ratio of the adjacent side length to the hypotenuse, and the adjacent side length is what I'm trying to find here in red. That means the side length here in red I'm trying to find is going to be cosine alpha times cosine beta. Because cosine alpha should be the ratio of this adjacent side length to the hypotenuse. So in other words, it should be cosine alpha times cosine beta divided by cosine beta, and that gives me the red length of the line segment. Over here in blue, this is the sine of alpha times cosine beta, because the sine of alpha is the ratio of the opposite side length to the hypotenuse. In orange, this is just going to be sine of beta, because sine of beta is the ratio of the opposite side to the hypotenuse. In other words, sine of beta over 1. So all of this checks out, I hope. Now I'm going to draw another vertical line straight from here, straight down vertically to here. So that I've got another right angle here. And if this angle, let's call it gamma, so that gamma is 90 degrees minus alpha. That way the interior angles sum to 180 degrees, because 90 minus alpha plus alpha is 90, and then 90 plus 90 is 180. This angle would also be gamma according to the opposite angle theorem with these intersecting lines, and that means this one would also have to be alpha. So this is a similar triangle to here, and that's how I get the alpha angle up in the corner. And that's going to be important because because now I can try to pick a color I haven't used before. Now I can draw a horizontal line through here, this purple line, and create a new triangle. In this new triangle, I've got a 90-degree angle in the bottom left corner, the purple line as the bottom of the triangle, the orange line as the hypotenuse, and the sort of maroon line in vertical, or a segment of the maroon line in vertical as the height of the triangle. So what is this height? Again, I'm sort of running out of colors I haven't used before. What is just this height here? That would be the adjacent side of this right triangle, the side adjacent to the angle alpha. And so I'm thinking about cosine alpha. If cosine alpha is the ratio of this length to the hypotenuse, sine of beta, then this length here in teal, this vertical length, would be cosine alpha times sine of beta. And now I feel like we are finally prepared to write down the formula for sine of alpha plus beta. Because sine of alpha plus beta is going to be the ratio of the opposite side, which is this vertical maroon line, the whole one that goes from the horizontal black line all the way up to the top of this triangle here. That is going to be the opposite side length, or the side opposite the angle alpha plus beta. And my hypotenuse is this green line segment, and the green line segment has a length of 1 for the hypotenuse. And so I don't have to worry about dividing by 1. Instead, what I have to do to get this vertical line segment, which is going to be the sine of alpha plus beta, that's going to be, first of all, sine of alpha cosine beta from right here. And it's also going to include this cosine alpha sine beta. And that is my geometric argument and my proof of the angle sum identity for sine. What I have left to show you is the angle sum identity for cosine. And cosine is going to be the adjacent side length of this right triangle. In other words, the side length adjacent to alpha plus beta. And it's not going to be this entire red side length, but it's going to be a smaller part of this. In other words, I'm looking for this. This purple is going to be the cosine of alpha plus beta. And so my strategy now for finding the cosine of alpha plus beta is going to be starting off with this longer red side length, which is cosine alpha cosine beta, and subtracting something away from it. What am I going to subtract away from cosine alpha cosine beta? Well, I would like it to be something like this. This length in here, from that point to that point, along that horizontal purple line, this tiny little purple horizontal line segment, that would be the difference here. So if I take red minus lime green, I should get the purple length. And so in lime green, that is going to be the side length opposite the angle alpha in this triangle that has hypotenuse sine of beta. And so the ratio of opposite over hypotenuse is going to be sine of alpha. And then, of course, times the hypotenuse, which is sine of beta. So this part is sine alpha, sine beta. To get cosine of alpha plus beta, I'm going to take cosine of alpha times cosine of beta minus sine of alpha sine beta. And so that is going to conclude our proof of the angle sum identities for both sine and cosine. So what I do know is that the cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And if we just choose to set beta equal to alpha, say those are the same angle, now I've got cosine of 2 alpha is equal to cosine alpha squared minus sine alpha squared. Do you see how that happens if I set the betas equal to alphas? Because if you're ever asked to prove the double angle identity for cosine and you're allowed to use the angle sum identities, yeah, just make beta equal to alpha. Now you've got 2 alphas. And the cosine of beta becomes cosine of alpha, and you're just squaring that, and then sine of beta becomes sine of alpha. You're just squaring that. That's the double angle identity for cosine. It's a very neat and short proof. once you have the angle sum identity. Anyways. And you can combine this. Well, let me see what's coming up next to my notes, and I'll scroll back up for you. Yeah. You can combine this with the Pythagorean identity, which says cosine squared of theta plus sine squared of theta is equal to 1. To do two different things, really. Number one, if I were to set cosine squared theta equal to 1 minus sine squared theta, right? Because I could just subtract sine squared from both sides over here. Well, then this is also equal to 1 minus 2 sine squared alpha. Alpha, theta, doesn't matter what symbols we use, right? But alternatively, I could go over here to my Pythagorean identity, and I could try to solve this for negative sine, which means cosine squared theta minus 1 equals negative sine squared of theta. So if I add that here instead of having the negative sine, I could also write that cosine of 2 alpha is equal to cosine squared plus cosine squared minus 1, which would give me 2 cosine squared minus 1. So there's three identities that you often see as the double identity angle for cosine. Sometimes you see this one, sometimes you see the one in orange, and sometimes you see the one in blue. It depends on what you're trying to do, what you're trying to accomplish with your trig identities here. So in the next step, where it says we want the power reduction identity for sine, how do we prove this, that sine squared of theta is equal to 1/2 1 minus cosine of 2 theta? Well, we just saw that cosine of 2 theta should be equal to 1 minus 2 sine squared theta. That was here in orange, 1 minus 2 sine squared of theta. So solve this equation for sine squared, right? What I mean is we got 2 sine squared theta is equal to 1 minus cosine 2 theta, and then divide both sides by 2. And when we divide both sides by 2 or multiply both sides by 1/2, then we get the identity we're trying to get. So again, a nice short proof that we're slowly building up by putting together trig identities. We saw this limit before when we were discussing limits, but I want to show you again because I think it's a really nice, important limit. And the way that this proof goes is like we draw a picture of a triangle. And for this triangle, the hypotenuse is going to be 1. I'm going to have a right angle, and I'm going to have this angle x. We are going to set this triangle inside of the unit circle, if you will. So that, imagine I've got a circle with a radius of 1. So that green circle is my unit circle. And the radius of that circle is 1. And the other picture that I'm going to draw here is a tangent line from the circle out to here. And that's not as vertical as I would like it to be. Oh shoot, that's the whole triangle. Yikes. That's slightly better. All right, what's this vertical length here? In orange, what's that vertical height? Sine of x. Now, since this is a circle with radius 1, and I'm taking a little arc length out of the circle, right here in green, if x is an angle in radians, and radians, if you didn't know, is just by definition like how many radiuses of the circle you're closing around, then the radius is 1, and that means the length of this green arc is x. That's just the definition of what it means to measure an angle in radians. Because 2 pi radians is a full circle. Because the formula for the circumference of a circle is 2 times pi times r. And here we're just taking x radians. And so if x is in radians, then x divided by 2 pi is sort of the fraction of the circle's circumference we're talking about. Then we multiply times the circle's circumference, and then the 2 pi's cancel. R is just equal to 1, and so that has to be x for the length of the arc. The last thing is, what is this purple? What is that purple length? That would be I don't know. That would be its own kind of right triangle here, where this is a right angle. And for this angle x, that would be the length of the opposite side divided by the adjacent side. What function gives me the opposite side divided by the adjacent side? Tangent. And so this side length here in purple is tangent of x. So we can see from the picture that sine of x is always going to be less than or equal to x, which is going to be less than or equal to tangent of x. Based on this little picture we've constructed. Because x is sort of sandwiched in between here. The sine of x is the straight path vertically, and so that's going to be the shortest one. Tangent of x is obviously larger than sine because it's the hypotenuse of this right triangle. And then this arc path is not quite as long as that hypotenuse because it's taking a slightly shorter path to get there. Next. What we want in the end is sine of x divided by x, and we want to use the squeeze theorem, so we want that thing in the middle. We're going to choose to divide everything by sine of x. And sine of x is going to be a positive number because we're in the first quadrant here. So if we divide by a positive number, then the order of these inequalities remains the same. So if I have sine of x divided by x, I get 1. And then x divided by sine of x will remain x divided by sine of x. And then tangent of x divided by sine of x is going to be 1 divided by cosine of x. We're going to take the reciprocal of all three of these terms. And in taking the reciprocal, that's going to switch the order of these inequalities. 1 divided by 1 is just 1. 1 divided by x over sine of x is going to be sine of x over x. And then 1 divided by cosine of x is going to be cosine of x. And you know, taking the reciprocal is going to flip the order of the inequalities, or the direction of the inequalities, because if I've got like 1/3 greater than 1/4, and I take the reciprocals, well, 3 is less than 4. So taking a reciprocal means you're switching the direction of the inequalities. And then the last thing is we take the limit. So if I were to take the limit as x approaches 0 of all of these things, well, the limit of 1 as x approaches 0 is 1. What's the limit of cosine of x as x approaches 0? In other words, what's cosine of 0? What's cosine of 0, you guys?
Yeah.
It's 1. So by the squeeze theorem, if I say the limit as x approaches 0 of sine of x over x is less than or equal to 1, and at the same time greater than or equal to 1, the only possibility is that this limit is equal to 1. So that's how we know for sure that the limit of sine over x is equal to 1. That's kind of the geometric argument, the proof here, that this limit should be equal to 1. Here's another important limit that we're going to need. And for this limit, we're going to have to use one of our trig identities that we discussed earlier. So what I'm thinking about specifically is the double angle identity for cosine. And actually, there was 3 different double angle identities for cosine. The one I'm really thinking about would have the sine squared in it. In fact, maybe even a better place to start is the power reduction identity for sine. So my power reduction identity for sine said something like this. Sine squared of theta is equal to 1/2 1 minus cosine of 2 theta. That's something we sort of proved above. And the reason I want this is because that means 2 sine squared theta is going to be equal to 1 minus cosine of 2 theta. And now let's define x as 2 theta. And now we can begin getting started, with this proof, is to say that like 2 times sine squared of x over 2 must be equal to 1 minus cosine of x. Or negative 2 sine squared x over 2 has to be equal to cosine of x minus 1. So let's take that limit here. We are taking the limit as x approaches 0 of negative 2 sine squared of x over 2 divided by x. because I'm using that trig identity to replace cosine of x minus 1 with negative 2 sine squared of x over 2. And I'm going to divide the numerator and denominator by 2. And I'm also going to factor out one of the signs. So I'm going to have sine of x over 2 times negative sine x over 2. I'll put the minus up front. Divided by x over 2. So again, we're taking the limit as x approaches 0. And I'm going to go ahead and split this limit, because I'm allowed to split two limits where I'm multiplying them. All right, we're finally able to do this, I think. What is the limit as x approaches 0 of sine of x over 2 divided by x over 2? It may even help to do this. If theta is equal to x over 2, what's the limit as theta approaches 0 of sine of theta divided by theta? Leah, do you know this one? What's the limit as theta approaches 0 of sine of theta over theta?
Zero.
It's not 0.
Is it just theta?
It's not theta. Here's your hint. The limit of sine of x over x as x approaches 0 is 1. And it doesn't matter what symbols we use. We use theta, right? So sine of theta over theta, the limit as theta approaches 0, that's 1. Okay, this one. What's the limit as x approaches 0 of negative sine of x over 2?
That would be 0?
Yes. Because we can just directly evaluate. Plug in x equals 0, and this is sine of 0. What's sine of 0? It's 0. So that means the limit as x approaches 0 of cosine of x minus 1 divided by x is 0. So that's going to be an important limit for us. This limit as x approaches 0 of cosine of x minus 1 divided by x is going to be important, just like sine of x over x is important.
Do you need to remember the blue, the red, and the purple? For
Yeah.
if there's not
Yeah, if I asked you to prove this on a test, I would want to see the whole argument starting from your trig identity. And like, I'll say this, I'll try to remind you of this too. You might be like wondering, where do I start, right? Like, do I have to prove that trig identity? No. Like, if I ask you to prove something on a test, I will tell you what you're allowed to use, right? Like, if I were making a test question, I would say, please prove the following limit. You're not allowed to use L'Hopital's rule, but you are allowed to use this trig identity, right? And you are allowed to use the limit of sine divided by x. You know, I'll tell you what tools you're allowed to use from your toolbox on a test question when you're going to make a proof, but you'll be able to use the same tools we have in lecture. You can just use the same proofs from lecture and it'll work. So here's the big theorem we've been building up to, right? We're finally doing calculus. We haven't, you know, we guess we took some limits, but we're finally doing derivatives. And this is an important derivative, I think. How do we really know that the derivative of sine is cosine? Well, we start from the definition of the derivative. And that definition of the derivative would say that the derivative of sine of x is going to be equal to sine of x plus h minus sine of x divided by h. That expression in the limit as h approaches 0. That's the definition of what it means to take a derivative of sine. Then we are going to have to use a trig identity. And the trig identity I'm thinking of is the angle sum identity for sine, which is going to be sine of x, I suppose, times cosine of h plus cosine of x sine of h. That is an application of this identity where I just set alpha equal to x and beta equal to h. So we use that trig identity, and then we are going to rearrange this just a little bit. So that I'm going to take the first term and the third term in the numerator and factor out sine of x, because they have the sine of x as a common factor. So let me factor out that sine, and I can write something like sine of x times cosine of h minus 1 over h plus the second term in the numerator is cosine of x sine of h divided by h. So again, let me just recap. The first term and the third term have a common factor sine. So factor out the common factor sine, and then the first term just becomes cosine of h, and the last term becomes minus 1. So I've got cosine of h minus 1, and of course we're divided by h, so there's your h. The second term, cosine of x times sine of h divided by h, is right here. You see what happened? Everybody buy that? So this is a limit as h approaches 0. It doesn't care what's happening with the x. If I'm taking a limit as h approaches 0, then anything that only contains x, any of those factors can be taken outside of the limit. And then I'm going to have cosine of h minus 1 divided by h. And I can separate my limit too, where I have a plus sign. Okay. Somebody tell me, what is the limit as h approaches 0 of cosine of h minus 1 divided by h? 0. We just did that limit. So I have sine of x times 0 plus, what's the limit of sine of h divided by h? 1 plus cosine of x times 1. So all told, we get the derivative of sine is equal to cosine. But
wait, why is it not just like sine of x? Oh,
yeah, this would be sine of x times 0, because that limit is 0. And that limit is 1.
okay.
Yeah, so all told, we have to use a lot of little tools from our toolbox here. We got to take the definition of the derivative, and then we have an angle sum identity for sine. And then we factor out the sine, and we factor out the cosine, and we rearrange it here in purple. We separate our limits, we take the x's out of the limits, and then we had to prove these limits just so that we could use them here in this proof to get something that should seem really simple. I mean, it should feel like this is simple, that the derivative of sine is cosine, but it actually takes a lot of logic to prove that. It's not an easy thing to prove when you consider all the limits that built up to it. But a very, very important proof for calculus. Okay. If I wanted to prove that cosine of x is equal to sine of pi over 2 minus x, I'm going to first remember my angle sum identity, which says this is sine of alpha cosine beta plus cosine alpha sine beta. And then we set alpha equal pi over 2 and beta equal negative x, so that sine of pi over 2 plus negative x is equal to sine of pi over 2 cosine of negative x plus cosine of pi over 2 sine of negative x. Now, cosine is an even function. And what it means to be an even function, if you remember from college algebra, is that cosine of negative x is the same thing as cosine of positive x. It's symmetric in that way. It doesn't matter whether you go counterclockwise around the unit circle or clockwise around the unit circle with your angle, your x coordinate will remain the same. And that means where I have cosine of negative x, that's the same thing as cosine of x. What is sine of pi over 2? What's the sine of pi over 2 become? Sine of pi over 2 is 1. You should know that from your unit circle stuff. What's cosine of pi over 2? If you guys don't know sine of pi over 2, cosine of pi over 2 is 0 from your unit circle. And so that means sine of pi over 2 minus x is equal to cosine. And that concludes your proof. you want to know why cosine of x is equal to sine of pi over 2 minus x, you just have to use this angle sum identity again. All right, and that means if I ask you what's the derivative of cosine of x, I'm asking what is the derivative of sine of pi over 2 minus x. And the derivative of sine is cosine, as we learned. And then the derivative chain rule says I need to multiply by the derivative of the inside function. We learned about the derivative chain rule already, so we're allowed to use that. And this means I've got -1 times cosine of pi over 2 minus x. What is cosine of pi over 2 minus x? If I say u is equal to pi over 2 minus x, that means x would be equal to pi over 2 minus u. And that means I can write sine of u is equal to cosine of pi over 2 minus u. So if I see cosine of pi over 2 minus x, that would be equal to sine of x. And here I've got cosine of pi over 2 minus x. And so that is sine of x times -1 is negative sine of x. So the derivative of cosine of x must be negative sine of x. And to move on, we need more stuff like the derivative product rule. So we're going to prove the derivative product rule. Derivative product rule proof is going to go like this. Start with the definition of the derivative. And from my definition of the derivative, we can say that the derivative of this function, which is f of x times g of x, is going to be the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x divided by h. That's the definition of what it means to take a derivative of this function. And then we're going to add and subtract the same thing from the numerator. When I say I'm going to add and subtract the same thing, I need to think for just a moment about what that's going to look like. Okay, I think I've got it. I think it's going to be minus f of x g of x plus h. And then I'm going to also have to add f of x g of x plus h. But notice I haven't changed the value of this thing. Whenever I subtracted this and I add back the same number, it's like adding a total of 0. I haven't changed the net sum of what's happening because I subtracted and added the same value. But the reason I want to add and subtract the same value is because of this. Now in the first two terms in the numerator, I'm going to factor out g of x plus h. I'll show you what that looks like. It's going to be like this. And then now let's take a look at the last two terms in the numerator. And for these last two terms in the numerator, they have a common factor f of x. So let me factor out the f of x. And when I factor out the f of x here, I'm going to be left with g of x plus h minus g of x. So in this step, we took the first two terms, factored out the g of x plus h, and then we also kind of separated this fraction here where the plus sign is, so it's still divided by h. And then over on the right side, we factored out f of x, and because we separated the fraction here, we still keep the same denominator. We still divide by h. But this green is the same thing as the previous line. I just rearranged it a little bit to look nicer and prettier. Okay. Now, I'm going to use some properties of limits, like I'm allowed to take separate limits anytime I'm adding or multiplying anything. So I might want to take a limit of this first factor, and then the second factor, g of x plus h, and I'll split up the limit here where there's a plus sign, and I'm going to end up taking 4 limits in total. My least favorite part of doing limits is having to write the word lim over and over and over and over and over again. But yeah, I guess that's just part of the job. That's why they pay me. So I can write lim, 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 lim. Okay. Does anybody recognize what is that first limit? What's the limit as h approaches 0 of f of x plus h minus f of x divided by h?
0 over 0.
No, it's the f prime of x.
That's the definition of the derivative. That's the definition of what it means to take the derivative f prime of x. What is the limit as h approaches 0 of g of x plus h? Yeah, the h goes to 0, so I'm just left with g of x. Plus, what's the limit as h approaches 0 of f of x? Yeah, just f of x. There's no h's there. And then what is this limit as h approaches 0 of g of x plus h to minus g of x divided by h? That's the definition of the derivative g prime of x. And voila, that's how our derivative product rule came to be. Does that make sense? Do you guys like that? You love it. Okay. The next one is going to be the derivative quotient rule. And for the derivative quotient rule, we're trying to take the derivative of f of x divided by g of x. And we are not going to appeal to the definition of the derivative. We're going to use the tools that we already put in our toolbox. One of those being, I can say this derivative is the same thing as f of x times the reciprocal of g of x, right? 1 over g of x, which is the same thing as g of x all raised to the negative 1 power, because we know our properties of exponents here. And that means this would be the same thing as taking f prime of x times g of x reciprocal plus f of x times the derivative of the reciprocal of g of x. Because this is the product rule, and we just proved the product rule. So now we're allowed to use the product rule. And the first part now is f prime of x divided by g of x, because dividing is the same thing as multiplying by the reciprocal. And then the second part is going to be f of x times, well, the chain rule, right? We already proved the derivative chain rule earlier, maybe last week, I don't know. Yeah, it was last week at some point. But the derivative chain rule says first I'm going to take the derivative of the outside function, which is just the power function x to the negative 1, and then I'll take the derivative of the inside function and multiply. So using the derivative chain rule, this derivative of the outside function is going to be negative 1 times g of x to the power negative 2, and then I have to use the chain rule to multiply times g prime of x, the derivative of the inside function. So as I'm proving the derivative quotient rule, I'm using the derivative product rule, and I'm using the derivative chain rule. And so now I have f prime of x divided by g of x plus, or maybe I should say minus, right? Because there's a negative 1 in there. If I'm multiplying by a negative 1, I might as well say minus. F of x times g prime of x divided by g of x squared. Because a negative 2 power means I can put that in the denominator, because multiplying by a reciprocal is the same thing as dividing. Dividing is the same thing as multiplying by the reciprocal. And I'm almost there. I'm almost at my answer here. The last thing that I need to do to get the familiar form of my derivative quotient rule is to find a common denominator. And finding a common denominator means I multiply this first fraction by g of x over g of x. And that way I can get my final answer, which is going to be f prime of x times g of x minus f of x times g prime of x divided by g of x all squared. Or as I like to remember it, f prime g minus fg prime divided by g squared. But that's my proof of the derivative quotient rule. And I like a proof like this where you don't have to go back to the definition of the derivative, because we've already proved other things, like we already proved the product rule and we already proved the chain rule. Now that we've proved the derivative quotient rule, we can use the derivative quotient rule to prove that the derivative of tangent is secant squared of x. And the proof proceeds like this. We're taking the derivative of tangent, which is the same as taking the derivative of sine divided by cosine, which you remember from trigonometry. And then using the derivative quotient rule, and I remember the derivative quotient rule as being this f prime g minus fg prime divided by g squared, where f is sine of x and g is cosine of x, obviously corresponding to the numerator and denominator, we're going to get the derivative of sine, which is cosine of x, times the denominator, which is cosine of x, minus the numerator, which is sine of x, times the derivative of the denominator, and the derivative of cosine is sine. And notice that we've proved already the derivative of sine, we've proved the derivative of cosine, and I forgot that whenever you take g prime here, meaning we take the derivative of the denominator, the derivative of cosine is negative sine, and two negatives make a positive, right? Because there's a minus sign here, and the negative we get from the derivative is going to allow me to write cosine of x squared plus sine of x squared here in the numerator. And then we are dividing by cosine of x squared. Now we remember from earlier in this lesson that cosine squared plus sine squared is always equal to 1 squared when they have the same argument. And then of course, according to the definition of secant, secant is the reciprocal of cosine. In other words, secant is equal to 1 divided by cosine. And so if I see 1 divided by cosine squared, that's the same thing as secant squared of x. And that's how the proof looks for the derivative of tangent. We're starting to develop some momentum in terms of like we have enough tools in our toolbox now to prove all of the derivatives we need. We don't ever have to return now to the definition of the derivative because we have a lot of things like the product rule and the quotient rule and the chain rule to build up from, as you saw in that example. So now we're trying to prove the derivative of arctangent of x is 1 divided by x squared plus 1. And the proof goes like this. We begin by recalling that tangent of arctangent of x is the same as x. And if you're wondering why, it's because arctangent is defined as the inverse function of tangent. And whenever I compose two inverse functions, I always get back the identity function, which is x. So this is true by definition. In the next step, we are going to take the derivative with respect to x of both sides. So I'm taking the derivative of tangent of arctangent of x. And on the right side, I'm taking the derivative with respect to x of x. On the left side, we'll need to use the derivative chain rule, which says first I take the derivative of the outside function, and the derivative of tangent is secant squared, while leaving the inside function alone. And then I multiply times the derivative of the inside function, which is the derivative of arctangent. And I don't know what the derivative of arctangent is yet, but I do know on the right side of the equation that the derivative of x with respect to x is 1. And now I can proceed if I divide both sides by secant squared of arctangent of x, so that the left side is the derivative of arctangent, and the right side becomes 1 divided by secant squared of arctangent of x. Now that is a way to describe the derivative of arctangent, but you'll notice that it doesn't match exactly what I'm trying to prove. It doesn't match 1 divided by x squared plus 1. So how do we get that form of my derivative? And to do this, we just need to draw a picture of a triangle. And in the corner of this triangle, I'm going to name this angle theta. And then I'm just going to kind of arbitrarily label these sides x and 1, and then the Pythagorean theorem would imply that the hypotenuse is the square root of x squared plus 1. Think about that for a moment. The Pythagorean theorem says this hypotenuse of this right triangle is going to be the square root of both of the sides squared. That means the tangent of theta is opposite over adjacent, so x divided by 1, and the tangent of theta is x. Well, what would be the result if I were to take the arctangent of both sides of this equation and the arctangent of the tangent? I'm composing two inverse functions. Those cancel each other out, and I just get theta. And on the right side, I find that theta is equal to the arctangent of x. So now I can write that the derivative of arctangent is 1 divided by secant squared of theta. And secant is the reciprocal of cosine, so now I can say that the derivative of arctangent is cosine squared of theta. Well, look back at my triangle. If cosine is the adjacent side divided by the hypotenuse, because that's the definition of cosine, the ratio of the adjacent side over the hypotenuse, well then let me replace cosine with 1 divided by the square root of x squared plus 1. And don't forget I had cosine squared. And now I'm ready to write my answer, because the square root and the square will cancel each other out. And my final answer is 1 over x squared plus 1. That is how I write the derivative of arctangent of x. And that's exactly what I was trying to prove. I'll show you one more of these examples, but anytime you have an inverse trig function like arctangent, arcsine, arccosine, arcsecant, arccosecant, arccotangent, the proof remains the same. You get the same exact strategy. So I'll do one more of these, and I'm going to leave the rest of them for you to do on your homework, so you can work through those independently and see how it works out. But once again, just like before, I'm going to be taking the derivative of not just arcsine, but actually sine of arcsine of x. And because sine of arcsine of x is a composition of functions, I just get back x. And so to balance my equation and do the same thing on both sides, I'm taking the derivative. This should look really familiar if you just watched me do the previous problem. On the left side, we're using the derivative chain rule to say the derivative of sine is cosine. And I leave the inside function alone for right now, which is arcsine of x. And then I multiply times the derivative of the inside function, which we don't know yet. This is going to be the derivative of arcsine of x. And on the right side, the derivative of x with respect to x is 1. So now I rearrange this equation by dividing both sides by cosine of arcsine of x. And I find that the derivative of arcsine of x will be equal to 1 divided by the cosine of arcsine of x. Again, this is not exactly the form that we're trying to find. We're trying to find 1 divided by the square root of 1 minus x squared. And this is a way that you could describe the derivative of arcsine, but it's not exactly the same as we would like. It's equivalent, but maybe it's not as pretty. And so we will once again draw our triangle, the triangle that has the angle theta in the corner and the right angle in the bottom right corner here. And we have to think about how I'm going to label my sides. Because what I want is that this is going to be cosine of theta. In other words, I want theta to be equal to arcsine of x. And that means sine of theta should be equal to sine of arc sine of x, or sine of theta should be equal to x. Sine is going to be the ratio of the opposite side to the hypotenuse. And so if I labeled my sides as x and a 1 for the hypotenuse, well, now the side opposite theta is x and the hypotenuse is 1, so sine of theta is x divided by 1, or sine of theta is x, and that's what I want here. I want that so that I can have 1 divided by cosine of theta. Very good. Now in my triangle, I need to find out what is this missing side, and the Pythagorean theorem is going to dictate that this missing side should be the square root of 1 minus x squared. And if you're not sure how I did that, pause the video and work through it a little bit. Write down the Pythagorean theorem with the missing side and rearrange the equation until you're convinced that this missing side should be the square root of 1 minus x squared. And now what is cosine of theta? Cosine of theta is the ratio of the adjacent side to the hypotenuse. And so it's the square root of 1 minus x squared divided by 1. Divided by 1 doesn't change anything. And so I'm going to replace cosine of theta with the square root of 1 minus x squared from my triangle. And that, everybody, is how you prove the derivative of arc sine is 1 over the square root of 1 minus x squared, which is what we desired to prove. And again, I really hope that that proof feels very much like the proof of the arctangent derivative. Do you see how similar it is? Step by step, it's the exact same steps. And so I'll leave you with one more thought, which is a little bit abstract, but let's call this the derivative inverse rule. Since the arctangent was an inverse function and the arcsine was an inverse function, this is going to feel familiar. If I wanted to prove this rule, which is telling me about the derivative of an inverse function, I'm going to first remember that if I compose the original function with its inverse function, the definition of what it means to be an inverse function is that function composition will give me the identity function, which is just x. And then I take the derivative of both sides. So here's the derivative of that composition on the left side, and then the derivative with respect to x of x on the right side. And we proceed on the left side according to the derivative chain rule, which means I take the derivative of the outside function while leaving the inside function alone, and then I multiply by the derivative of the inside function, which I don't really know yet. I don't know what the derivative of the inverse function is yet. But on the right side, I do know that the derivative of x with respect to x is 1. And now, let me rearrange this equation by dividing on both sides by f prime of f inverse of x. That is what we desired to prove.